welcome to Mrs. Mahoney's podcast. This is our second one of Unit 10. So I'm at the top of page 6, and we just really have some more vocab to go through, and then we're going to look at called a solubility chart and kind of learn how to read a solubility chart. So first, let's look at some of the vocab. And we're talking about still the solutions, and now we're talking about how something dissolves and how can we make it dissolve faster, or make it maybe dissolve a little bit more efficiency. So this is all talking about that solubility. I have some examples I'll probably show you in class. For a lot of times, use what you know. And what do we probably know here in the South? Tea. So when you're dissolving something, what dissolves sugar better? Hot tea or cold tea? So temperature usually helps. So again, temperature means heating the solvent is usually going to increase the solubility. And that's what we're going to look at that chart. Notice that we're saying usually, and we will see on the graph that not all solids affect this way. And also when we're talking about this, when we're talking about these factors, we're talking about solids dissolving in a liquid. And so usually temperature, think of your hot tea. Well, what else do we know? We know that if I increase the surface area, that means crushing it, that you're going to have it dissolve faster. Well, what dissolves faster? A sugar cube or powdered sugar? Powdered sugar dissolves faster. And the whole reason is this is my molecule that's being dissolved. Here's my little water molecules. The more these can come in contact, the faster it's going to dissolve. So if you heat the temperature, that means everything's moving faster, so they're having more collisions. If I increase the surface area, I've just increased the area that I can have more of these collisions. And remember, when something's being dissolved, they're being surrounded by that water molecule. So the more I can have them come in contact, the faster they can dissolve. And then agitating means stirring. And the same thing, if I will increase the solubility, increase the rate. When you dump sugar into your tea, what's the first thing you do? You start stirring. You need to know, what does agitate mean? Agitate means to stir, because I would imagine that you're going to see more likely to see the word agitate than the word stir when it comes in talking about solubility. You need to know the vocab, the chemistry vocab, and even the non-chemistry vocab. Okay, so again, solubility. I have this just kind of at the top. Make sure you know the definition. Solubility is just how much solute can I dissolve in a solvent. So how much solute can be dissolved in a solvent? We talk about its solubility. And I think if you even know commonly, if you've spent any time in the kitchen, you should know that you can dissolve more sugar in the same amount of water than you can salt. Sugar has a higher solubility than salt. I can dissolve more. So the vocab that we say, if we say in a solution is unsaturated, that means it contains less solute than the maximum. So this is like than the maximum. What does that mean in common words? It means you can dissolve more. It can still dissolve more solute. I haven't reached that maximum solubility. So an unsaturated solution contains less than the maximum amount. So a saturated solution means it contains that maximum. It means that no more solute will dissolve. So no more solute will dissolve. I throw it in, I stir it, and I stir it, and I stir it, and it's not going to dissolve. Now the key thing here is at the same temperature. If I change temperatures, then I'm going to change conditions. So I'm saying without heating it, it no more will dissolve. So if I have an unsaturated solution, I throw some in and I'm going to stir it, it's going to dissolve. If it's saturated, I throw in more salt, I stir and stir, it's just going to sit at the bottom. So you will see particles sitting at the bottom of a saturated solution. That's how I can tell that it's saturated. When I look at it, you're going to see some solute particles that did not dissolve because it couldn't fit. It was full. Okay, then this is a special case. We can't always make this. This is a special case. So don't think all solutions are supersaturated. I force it. I can contain more solute than it should, and again, under normal conditions. The way we force this is usually I can heat it, because I'm going to show you, and again, if you notice there it says I'm going to show you an example. I force it, so I heat up and put a lot more in there than it should, and then I let it cool really slowly. So it's a very unbalanced situation that it's very easy to get unbalanced, so hopefully these work. But I have forced it to dissolve a lot more than it should. It's super saturated. Okay, so those questions, looking back at that, if I look back, what happens if a crystal is added to a saturated solution, unsaturated, supersaturated? I want you to think about those and answer, and especially after we look at the demo tomorrow, we'll come back and talk about those questions, but I want you to answer those 3 questions and to think about what that would look like, and then we'll try to see that in lab in the demos tomorrow. Okay, so down towards the bottom, dilute and concentrated. Dilute means there's very little solute is dissolved in the solution. Kind of another way to think of it, this means that it's kind of a weak solution because there's not very much in there. If you've ever made Kool-Aid and you didn't follow the recipe and you didn't know what a quart was versus 2 quarts, and you put twice the amount of water and to the same amount of Kool-Aid, then you know that it's going to taste pretty weak. That's a dilute. Okay, opposite. Again, you did it backwards. You doubled it, but forgot to double the water. You tasted it, concentrated. They are what you would think of as like strong. Now, don't think of this when we turn them to acids. This won't necessarily mean strong and weak acids, but for concentrated, think of concentrated juice. Have you ever seen those frozen juices? They're very, very concentrated. There's a lot in there. What do? You dilute them down to where you can drink them, the ones that you get in the freezer. So then there's another question. When can a solution be saturated and dilute? That's another good one. I want you kind of thinking and puzzling and seeing if you can give me an answer. And I'll be honest, probably after we look at the solubility charts, then I would go back and maybe think about that question, because that might help you to question that. Okay, 2 more vocab words we're going to kind of look at. Miscible and immiscible. Okay, this is when we're talking more about a liquid and a liquid, 2 liquids. So miscible is when those 2 liquids are soluble in each other. That means they're going to dissolve in each other. I throw them together, I do not see a line. They totally mix. So that means they totally mix. So that's why I put this. Miscible means mixable, something that helps you to remember what they mean. Okay, so if it's immiscible, then that's the 2 liquids that are insoluble. They do not mix. Oil and water. I think most of you have seen that. If you put oil and water together, you get 2 distinct lines. They do not dissolve in each other. But instead of saying they do not dissolve, we can say technically they are not miscible, or they are immiscible in each other. They do not mix. And then it's back to, we've talked about it once, and I said we kind of come back and talk about it. And there's that saying then, like oil and water. Like dissolves like, and that's referring to the polarity of the 2 substances being mixed. So again, polar dissolves in polar. So water is polar. It will dissolve other polar substances. And remember, water is so polar, it will also dissolve many ionic substances. So nonpolar will dissolve in nonpolar substance. So looking at oil and water, well, we know water is polar. Oil, and most organics, is nonpolar. So that's why when you put those 2 together, they do not mix. They're immiscible because they are 2 different polarities. They do not mix. You see them as 2 separate lines. And we'll look at some more things kind of with that. So a lot of it to say, can it dissolve? You have to figure out the polarity of the substance and compare it to the polarity of what you're trying to dissolve it in. Okay, let's look at a solubility graph, and you're going to be seeing these. You'll see them on tests, and yes, you're going to have a quiz using this. So we need to kind of figure out what the solubility graph is. Okay, and what this graph is, if we look at this, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 substances. Kind of highlight, if you look at this right here, let me change color so I can actually kind of see. Okay, right here. We're going to come back and kind of answer a question on this. This is ammonia. Ammonia is a gas. Okay, at the very top, what this is, I could have had 9 different graphs, or however many compounds are put on here. But for purpose of saving space, they just put all these different compounds on one graph. So sometimes the hardest thing is to find out, keep the line straight when you're reading this. So look at what this is telling me. It's telling me the temperature. So look at our temperatures going from 0 to 100. Okay, at 100 degrees, what does water do? Boil. Yep, you're right. So it's no longer a liquid. So that's why we only go into 100. Okay, you need to add this. Yours should say over here, grams of solute per 100 grams of water. This is important. It's grams of solute. And it's really important, this is for 100 grams of water. Now remember with these grams, a gram of water is the same as a milliliter of water is the same as a cubic centimeter of water because the density of water is 1. So sometimes we see these labeled in different labels, but this is what I'm interested in, how much water, because I know a gram is the same as a milliliter is the same as a cubic centimeter. I need to know that I have 100. Okay, so right at the top it says, okay, the solubility of most solids, what's happening to it? So look at this line. This is telling me how much I can dissolve potassium nitrate at each temperature. So as my temperature goes up, what's the slope of the majority of the lines doing? So hopefully you can say it's increasing. So I would say the solubility of most solids increase with the increase of temperature. Okay, so the way you would read this, look at question 1. It says, what's the solubility of a saturated solution of potassium nitrate at 10 degrees? So find 10 degrees. Okay, find potassium nitrate. Here's my potassium nitrate. So right here, this point. Okay, so the line is your saturation point. So if you're right on the line, that tells you how much it can dissolve. So you come up and where does that line cross then at 10 degrees? So on number 1, I would say that's around what? 22 grams of potassium nitrate in 100 grams of water. And the water matters because if I change the amount of water, I'm going to change how much it can dissolve. So everything on this graph has to be from 100 grams of water. Okay, now if I only had So look at this. If I only had 10 grams, I would have less than I could dissolve. That would be an unsaturated solution. If I was able to force 30 grams in it and said I dissolved 30 grams at 10 degrees, that would make it a supersaturated solution. So right on the line is saturated. If I have less than the line says I can, that's an unsaturated. If it says I have forced to have more than the line can hold, that would be a supersaturated solution. Okay, so look at number 2 then. What compound is saturated if 80 grams? Okay, make sure you keep them straight. You know, grams is on the X, the grams is on your Y, it's your vertical, and your temperature is on your X. So here's my 80 grams, and I want to know at 50 degrees. So come up, what compound is crossing that line? That would be KNO3. So on number 2, you would write down potassium nitrate or KNO3. Okay, and I'm just trying to give you samples of all these different kinds of questions you could see. Look at number 3. At what temperature would a solution containing 40 grams potassium nitrate and 50 grams of water be saturated? Okay, sometimes you're going to have to do a little bit of math because look at what this one is saying. It's saying that I want to have 40 grams in 50 grams of water. But to use my graph only tells me about 100 grams of water. So you have to keep everything in the same proportion. So if I double my water for my graph, then I need to find 80 grams of KNO3. Where can I dissolve 80 grams of KNO3? So use your graph, 80 grams KNO3, there's that same point right there. There's that same point right there. What temperature is that? That's 50 degrees. So your answer for number 3 then would be 50 degrees Celsius. Okay, so let's look at question number 4. Now there's two different things happening in number 4. First, I'm cooling it. So when you see something cooling, that means you're going to have to compare how it can dissolve at a higher temperature compared to the amount that can dissolve at the lower temperature. So that's one thing I have to look at. Second thing, look at my water. I have a different amount of water, so I have two different things. So if we can do this, you can pretty much do any of the problems that you're going to be seeing. So let's just kind of compare to the 100 grams of water. Let's ignore that 200 grams for right now. Let's look at the first part that says at 100 degrees, how much can I dissolve compared to the 20 degrees? So KCl right here at 100 degrees. So let's just say in 100 grams of water at 100 degrees, how much can dissolve? And that's what? I'm going to say that's about 56 grams. Oops, I need to have my 6 there, don't I? 56 grams. Okay, compared then at 20 degrees, because this is what we're saying. We're taking this and we're going to cool it down. Well, at 20 degrees, it can only dissolve, and again, I'm estimates from here, about 32 grams. So look at the difference. I can dissolve much less at the cooler temperature. So what's going to happen then as it cools, it's going to start crystallizing out or precipitating out. You're going to see that solid start to come down on the bottom because I cannot dissolve as much. So what is 56 minus 32? That's 24 grams will come out of solution. Okay, but this is in 100 grams of water. Okay, now if we look at this, so it's saying I'll have 26 grams out of 100 grams, but I said I had 200 grams. Double the water, so what does that mean? Wait, it would help if I could subtract too. That's not 26, that's 24. I had the 6 in my head. Sorry, so that's 24. So if I double that, that would be 48 grams will come out of solution or will crystallize in every 200 grams. So when you're using these charts, you just really have to be careful to see the water. And if you ever give two temperatures, you're going to compare and you're subtracting to see what the difference is. It could either say how much more do I need to add or how much is going to be crystallized. Those are the two ways that we can see two different temperatures. They're just asking you compare the amounts between the two temperatures. Okay, so look at even number 5. How much sodium nitrate must be added to make a saturated solution? And again, in 50 grams at 10 degrees. Okay, so we've got my 10 degrees. Okay, I want to find sodium nitrate. Sodium nitrate is NaNO3. Come up, where's across the line? So right here, and let's make our math easy. Let's just go ahead and call that 80. So at 80 grams, and so that also means on a quiz, I usually give you that plus or minus 1 gram or 2 grams. Some of you will say, no, that's 79. You want to be more technical. I'm going to say, okay, that's close enough to 80. I give you that plus and minus as long as I can see where you've gotten your numbers. So what is this saying? This is saying I can dissolve 80 grams of sodium nitrate in 100 grams of water. But it says I only have 50 grams of water. So if I have half the water, I can only dissolve half the amount of substance to keep it saturated. So there's your number. Your answer would be 40 grams of sodium nitrate. So obviously if you said 79, it would be half of your 79. Okay, and so then I want you to answer this last question then. How does the solubility of gases compare to solids? So right here I said point this out. Again, here's my ammonia. So how does that solubility compare? Yep, you're right, it's opposite. And you've seen that if you've ever, which I totally do not recommend you doing, leave a unopened bottle of soda in your car on a hot summer day. If you've ever had that soda explode, you've seen that relationship. Because what happens is the carbon dioxide that's been dissolved in there, as that temperature gets hotter and hotter, less carbon dioxide can be dissolved. So therefore it's escaping, and if you notice there's just a little bit of space left above the liquid for gases to come out of solution, and if it gets too hot, too much gas is coming out, you increase the amount of pressure, and a lot of times, or many times, your bottles can explode. So it has nothing to do with the liquid. When a bottle explodes on a hot day in your car, that's because of solubility of gases, and you've reached the point where the carbon dioxide cannot dissolve in the gas. Okay, so for the next couple days, we're going to be dealing with these graphs and talking about how temperature and solubility affects different things. I will see you tomorrow.